Assalamualaikum warahmatullahi wabarakatuh, and have a nice day. Today we're going to continue the last topic for chapter 2, which is a multistage amplifier specific in the Dalington connection. Dalington pair, the configuration similar like cascade configuration. However, this connection have no capacitor in between two transistor. Second is Q1 or transistor 1 and transistor 2 connected at the base, at the emitter of transistor 1 connected to base for transistor 2, and then they have same connection at the collector 1 and collector 2 leg. The advantage for this configuration, Dalington pair can provide high current gain, so we can conclude that the IC or current output that we produce equal to or similar to beta power of 2 times with our input current IB. So the relation between those most of calculation related on the current flow. So the tip to start this configuration, you must start at the first transistor Q1 and start with IB. So we call this IB1. So IB1, from the IB1 we can compute IC1 by implement beta IB. And then third, we can find the IE1 by using 1 plus beta 1 times IB1. At the same time, this leg share with second transistor leg, which is from emitter transistor 1 connected to base transistor 2. So we can say that IE1 equal to IB2, and then those of current share the same formula. Okay, after we got the IB2, now we can find for IE2. The first step, we can find the IE2, where IE2 equal to 1 plus beta 2 IB2. Then we can replace IB2 with the previous formula of IE1. So it equal to 1 plus beta 1 times 1 plus beta 2 IB1. The fifth step, you can find that if we get the IB2, now we can find IC2. IC2 is equal beta 2 times IB2, where you replace the IB2 formula inside the equations. So you got beta 2 times 1 plus beta 1 IB1. Alright. Like I said, these two collectors are meet at the same junctions. So the total, we can say the total IC equal to IC1 plus IC2. So by add up formula that we already get, then we can find the IC total equal to beta 1 plus beta 2 times 1 plus beta 1 and times by IB1. If the question given the beta 1 and beta 2 is equal to same value, for example 100, so we can assume beta 1 beta 2 with the same beta. So like I said that IC total equal to IC1 plus IC2 by replace the equation given and you open the bracket, and then you can find that the IC equal to IB times 2B plus beta square, whence we assume the B1 and B2 are equal. So since beta is equal, or example here we give the 100, you replace the 100 inside the beta, you can find that IB with times with 2 times 100 plus 10,000, so means that the 100 here is too small compared to 10,000, so we can ignore this value of 2 beta or 200 here. That's why we assume that our IC is equal to IB times beta square. So we ignore the 2 IB here. It because the value 2 IB is too small compared to beta square IB. Alright, we settle with the current distribution to Dalington configuration. Now we try to convert our transistor Dalington configuration into the small signal. Alright, how we do this? First, keep in your mind, we start with base to emitter at the transistor 1 in this area. In this area, we start with R pi. Between base to emitter, we have R pi. So at the R pi, we know that it has voltage, we call V pi 1. So at this connection, we already done. Then from the emitter 1, it will be connected to base 1, base 2. Right? At the base 2, connected with the emitter 2. Between base 2 and E2, we have another R pi, we call R pi 2, and absolutely he has a voltage, so we call the voltage V pi 2. Alright, and then connected to end of emitter leg for transistor 2. Alright, this area also done. Alright, let's back to base 1 to collector 1. From the base 1, we continue with collector 1 to emitter 1. At the leg of collector 1 to emitter 1, we have a current, so they call GM1 V pi 1, the diamond one. Alright. Okay, settle this collector to emitter 1. Now we try to solve the leg of collector 2 to the emitter 2. So we have another collector. At this junction, we have collector 1 connected to emitter 2 with the diamond current. So we name it as GM2 V pi 2. And at this point, we connected to the total collector. From these configurations, we can conclude that this Dalington pair can provide increased current. The increased output current means that this configuration is suitable to gain up our current output, and this configuration also has high input resistance. It's very high input resistance for the this amplifier Dalington configuration. Let us find the small signal relation for this Dalington pair configurations. Alright, they have us because we want to gain up our output current, so we inject our input with the input current. So we name is I or I input, current input. So this current will entering the RPI 1. So when current times with resistance, so it produce our voltage. So we produce the voltage V pi 1. Okay. So from these relations, the current of GM V pi, we can transform it by replace V pi equal to I1 R pi. So it become GM1 I1 R pi. Since the formulas of beta is equal GM R pi, so we can conclude that GM1 R pi 1 equal to beta 1 time with I1 is equal to our GM1 V pi 1. So you can replace the GM1 V pi 1 equal to beta 1 I1, beta 1 II. Okay, so this also I. Both of current beta I and current I will entering the current on base 2. So we can conclude that current IB2 or current base 2 equal to II plus beta 1 II. So we can simplify, bring out the II. So it equal IB2 is equal II times 1 plus beta at this total current. So at the same point, we can conclude that the current insert at the R pi 2 we produce V pi 2. So we can say that V pi 2 is equal IB2 times R pi 2, where the V pi 2 is equal I in 1 plus beta times R pi is equal to V pi 2. Alright, we can conclude that from the previous configurations, we know the V pi 2, V pi 1 is equal to I R pi y, R pi I, R pi 1. So from the V pi 1, we can replace inside the GM V pi 1. So we got an equation for GM V pi 1 is equal to beta 1 II. It's also together with IB2. The IB2 we just found that IB2 is equal total current II plus beta 1 II. And then from this current, we know that current IB2 times R pi 2, we can compute the V pi 2. So the V pi 2 finally is equal to 1 plus beta 1 II R pi 2. And then from these relations, we can replace V pi 2, insert the GM to V pi 2. Then new GM to V pi 2, we replace the V pi 2 equal to 1 plus beta 1 II R pi 2. Then we rearrange so GM2 R pi 2 is equal to beta 2. So our current of GM2 V pi 2 is equal beta 2 plus times 1 plus beta 1 II. Okay. Now we can compute our total current output. The total current output at these junctions. So we call I out. So I out is current entering that will out at the point A, and the current out at the point B. So at the point A we have current GM1 V pi 1, and at the junction 2, at junction B we have GM2 V pi 2. So the total I out, by replace that GM V pi that just we found, then we replace the equation for GM2 V pi 2 that we just found, then we get that I out equal to beta 1 II, and we found that beta 2 1 plus beta 1 II. This is question for the total output current. This is a formula to find the total output current. Okay, let I stress on this configuration suitable to gain out the output current. So we just focus on the gain current. So gain current equal to I out over I in. So from the previous slide, we can conclude that our I output equal to current at the point A plus with current at point B. So I out equal to beta 1 IB plus beta 2 times 1 plus IB I in over I in. So we can cancel the I in. The final gain current equal to beta 1 plus beta 2 times 1 plus beta 1. When you open the bracket, we get beta 1 plus beta 2 plus beta 1 times beta 2. So like I said, when we for example, we put the value for the beta, and we found that beta 1 plus beta 2 is equal to very small value for gain, but the beta 2 times beta 1 they produce very high gain. So we can ignore the 1 plus beta 2. So we assume beta 1 plus beta 2 equal to 0. End up, our current gain is equal beta 1 times beta 2. Alright, besides to find our current gain, sometimes the equations will ask us to find the resistant input or resistant output. To prove this configuration provide very high input impedance, so we try to search, try to find how to compute our resistance impedance or resistance input. So to find the resistance input located at base to emitter 1 together with emitter 2 base to emitter 2. So how to find this total resistance? So the best way is by find out what the total voltage between these two. So we name it as V input. V input is a combination between voltage at V pi 1 and voltage at V pi 2. So by replacing the equation V pi 1 is equal current input entering the R pi 1 and also the total current input at IB2 times with R2, R pi 2. So total at IB2 is equal 1 plus beta 1 II times R pi 2. So by take out all the current I and bring under the voltage, so we know that the Kirchhoff law said V equal to IR and resistance equal to voltage over current. So we bring out our current into the left side, and then we found that the resistance is equal to R pi plus 1 plus beta 1 R pi 2. So we can conclude that this total resistance in area from B1 until E2. So if you plug in the value, then you can find this input resistance for this Dalington configuration. To gain up your understanding, let's doing some exercise by given this value and the circuit. So the question asks us to find the Q pi, the Q pen, Q1 and Q2 means that you need to find IC Q1 and VCE Q1 for Q1, and you need to find IC Q2 and VEC Q2 for Q2. And then he asks to find the voltage gain, input resistance and output resistance. Right, since the AV, the voltage alert is infinity, so we know that R out 1 and R out 2 equal to 0 ohm. So we can avoid or neglect this resistance output. Okay, the circuit given like this. So first you need to do DC analysis. So you need to implement rule IC analysis said that when you have capacitor, you need to open, and AC voltage source you need to short. So when short here and open the circuit and open this circuit, so this line will be neglected. And then now we need to identify what the voltage inserted into base, so we call VBB or VTH. And then we need to find the resistance entering the base, so we need to find RTH or RBB. Okay, let's find it. So to find VBB, the voltage entering in the base, so the voltage is located at the R2. It because from 10 volts will be deduct at this voltage V1, and then the drop voltage V1, then the balance of VCC and V1 is the voltage entering the VB, the voltage entering the base. So that's why we use the voltage divider formula by putting R2 at the top. Then you replace the value 125 times 335 times VCC, then you got the value 2.72 for the VBB. And then the resistance input, the base is located at between R1 and R2, so means that it's parallel. So the RBB is R1 parallel R2, and then we got the value of 91 kilo ohm. Then transform this circuit into simplest one like this. Okay, from this circuit we can make it, we can find the value of IB1. Like we already learned previous slide, the relation of this Dalington pair current distributions. So we just apply the formula. So to make, first of all you need to find IB by using this loop. So you can meet negative first, negative VBB plus IB RB plus we have VBE here, VBE1 plus VBE2 plus we have IE2 and RE2. Finally we find the ground, so equal to 0. By rearrange your equations, so we can say that IB1 RB1 plus VBE plus VBE, we have 2 VBE plus IE2 RE2 equal to VBB. Okay, since the IB2 equal to IB2 is equal to IE2, base current for the collector, the transistor 2 equal to current at emitter at transistor 1. So the relation is IE1 equal to beta 1 plus beta plus 1 times IB. So from this IB2 we can find the IE2. So IE2 is equal beta plus 1 beta 2 plus 1 IB2. So we just replace the IB2 here. So we got the value. Since the beta 1 and beta 2 is equal, so by replace this, we can say that beta 2 plus 1 IP2 is equal to beta 2 plus 1 times beta 1 plus 1 IB1, right? Since beta 1 and beta 2 is equal, so we can say that beta plus 1 power of 2 times IB1. Then we replace this IE2 inside our equations, inside here. So we got the new value for IE1. Okay, from this new relation, we can searching for value IB. Okay, you are replacing the value and then you can find the IB. So the total IB is equal to 0.128 microampere. So after you got the IB1, now you can find the IC1 and IE1, where the IC1 equal to beta IB1. So you got 12.8 microampere for IC1, and IE1 is located same at the IB2, so 1 plus beta IB1, we got the IE1 and IB2 equal to 12.93 microampere. Okay. Now after you got the IB2, you can find IE2 and IC2. So for the IC2 equal to beta IB2, by replacing the value IB2 and value beta, then you got the new value of IC2 is 1.293, and for the IE2 is equal 1 plus beta IB2, you got value for 1.3 milli. Alright, so we not stop at this point. We need to find the VCE, because we want to find the Q point. So Q point require IC and VCE. So to find the VCE, you need to find VE first. So for the VE2 located at resistance E2. So IE2 times RE2, we got VE. So this is VE2, and then for the VE1 is from this point until this point. So it equal IE2 plus we have VBE here. So IE2 plus VBE, so we got value IE1 equal to 2. Alright. So now we need to find the value of VCE1 and VCE2. Okay, if we see on the circuit, we realize that the location VCE1 and VCE2 are parallel each other. So we can say that VCE1 and VCE2 are same value. So VCE1 and VCE2 is balanced voltage from the total input minus with the voltage drop at RC. So what a voltage drop at RC? We name it VCR. So VCR you need to find the total current insert to the RC. So the total current is IC1 times IC2 is equal to total current of IC total. Alright, you already found that what the value IC1, IC2, just replace. So we assume the total current here times with RC, and then VCC total minus all this voltage drop or the RC. We found that VCE1 and VCE2 is 7.127 volt. Okay, after you found the VC1 and VE1, VC2 and VC2, we can find the VCE1 and VCE2 by for VCE1 minus VE1, so you got new value is 5.27, and for VEC2 you just apply VC2 minus VE2, so you got new value is 5.827 volt. Now you got the new Q point for Q1 and Q point for Q2 by matching ICQ1 and ICEQ1, for the Q2 ICQ2 and VCEQ2. Okay, next, after you find the Q point, you need to do this AC analysis. Rule said if you has capacitor, you need to short, and if you has a DC voltage source, you need to ground. Okay, now capacitor will be short, and second capacitor will be short, and voltage VCC will be ground. So since this line will be short, no current will be flow inside the RE. No current inserted RE, because total current will be used this way, the easy way, the way that has no load. Okay, from this you need to transform into simplest circuit. You can assume that transistor 1 connected to transistor 2, and then base connected to R2 connected with R1. Both are located connected to the ground, and then this connected to our source. Alright, and then this transistor 1 collector we connected with the collector at the transistor 2, and then it connect with the RC connect to the ground, and our emitter leg directly to use the shortcut way, so pass the resistance RE, and we have V out. Then you can convert this into small signal. So the result is okay. To find the AV, you need to use formula for voltage out times divided by voltage source. So what is V out? V out located at RC. So you need to find the current drop into the RC. The current drop into the RC is equal to I out. I out is equal to current at point A plus current at point B. So current at point A is GM1 V pi 1, and current at point B is GM2 V pi 2. So we total it up, and then we replace into the equation times VRC. Now we want to find the relation. We want to find the voltage Vs, but we need to find the relation Vs between V pi. So what the relation between Rs, Vs and V pi? Vs located at here, so it parallel between these two voltage. So we can say that Vs is equal to V pi 1 plus V pi 2. So what the V pi 2 is? V pi 2 is equal current entering R pi 2. So this current we call the I in, and this call this from the previous slide we can say that GM1 pi 1 equal to beta I. So it equal to current entering here I base 2 equal to II plus beta II. So 1 plus beta II. So P 1 plus 1 plus beta II times R pi 2, we got the equation for V pi 2. See, we know that is at the same situation, II entering here is equal to V pi 1 over R pi 2. Alright. By use this equation, you replace inside II, so you got new value for V pi 2. So V pi 2 equal to 1 plus beta V pi 1 over R pi 1 times R pi 2. So since at our V out we also have V pi 2, so the motivation here, we want to use only one term of V pi. So now we want to eliminate V pi 2 and become V pi 1. So we replace the equation that we found relation between V pi 2 and V pi 1. So we use this equation replace to V pi 2. So for the V out equation, we only has V pi 1 insert these relations. So we replace V pi 2 insert the equations. So like this, we got GM V pi 1 V pi 2 times GM2, and then we got 1 plus 1 beta R pi 2 over R pi 1 V pi 2 times RC. Okay, so we try to make both of side over R pi. So this side we need to times R pi 1 over R pi 2, R pi 1. Okay, so it becomes GM1 R pi 1 V pi 1 plus GM2 R pi 2, 1 plus beta 1 V pi 1 over R pi 1 times RC. Okay, so since GM R pi equal to beta, so GM1 V pi R pi 1 become beta 1 times V pi 1 plus beta 2, GM2 R pi 2 become beta 2, then times 1 plus beta 1 V pi 1 over R pi times RC. So we got the new equation for V out. V out equal to beta 1 plus 1 plus beta 1 times beta 2 over R pi RC times V pi 1. Okay, got this. Since I said Vs equal to V pi 1 plus V pi 2. So we replace our V pi 2 into the term of V pi 1. And then we can apply the formula V out over Vs. And then we can simplify. Both of side have V pi 1. So we can replace V pi 1. And we rearrange back. So R pi 1 become down. So 1 here times R pi become R pi. 1 here plus 1 plus beta 1. So okay, sorry. We eliminate V pi 1 and bring R pi 1 to going down. So R pi 1 times 1 plus beta 1 R pi 2 over R pi 1. So later on you can cancel the R pi 1 here. And finally, your V out AV become this equation, and just plug the value. All those value you already has. Beta also given, RC given, R pi you have count, R pi 2, R pi 1 and R pi 2 already count. And then you can found that this Dalington configuration produce minus 55.4, less than 100 gain. So means that the Dalington pair produce less gain compared to cascade. Okay, we still not finished yet. The question asks us to find the resistant input, because this configuration provide very high input impedance or very high input resistance. So the input impedance is RPB will parallel with total resistance at the transistor resistance, is parallel with the RPB. So we name this internal resistance transistor as RIB. So how to find the RIB? So you need to find total voltage V pi 1 plus V pi 2. So total voltage is V pi 1 plus V pi 2. So you know V pi 1 is current IB entering the resistance 1 times the IB. So we got the V pi 1 and V pi 2. So we got the total current inside the IB2 equal to 1 plus I1 plus 1 beta I in plus beta I in. So 1 plus beta I in times R pi 2. So you just make it total, and we can say that V over IR, so R equal to V over I. So you can bring the current at the left side. So V over current. So the left of the equation is become resistance. So resistance is R pi 1 plus 1 plus beta 1 R pi 2. Right? So you press the value, you get the R in base equal to 405 kilo ohm. Still not finished yet, because the total impedance, input impedance equal to RBB parallel with RIB. So you replace RBB parallel with RIB. So you got the total impedance, input impedance or input resistance is 73.6 kilo ohms. And for the output impedance or output resistance located here, so we only has RC here, so Rout is equal to RC, so Rout equal to 2.2 kilo ohm. Alright, okay, that's all. If you see here, our RIS or our input impedance, it's very large, equal to 73.6 kilo ohm compared to our output impedance is 2.2 kilo ohms. So means that our Dalington pair produce high input resistance, and then it also provide high output current gain. Alright, before we finish our lecture here, I need you guys to fill out the attendance. Okay, please scan the attendance here. Please scan attendance here and fill up your details. Alright, thank you guys for joining me this chapter. So we cover all the chapter for multistage. Alright, thank you guys.